Hello friends, in the last lecture we discussed about the first order systems, what is the significance of the time constant and the steady state gain, and we started discussion about the second order systems. So this was the second order system that we had written here, which we represented it as equation number 4. I missed to write equation number 2. This equation is actually equation number 3, sorry. Now let us continue where we stopped. So this we are aware of this equation. Linear second order systems can be represented by this d square by dt square plus 2 zeta omega n dy by dt plus omega square n y of t equals to k into omega square n into u of t. Here we know that zeta is represented as damping ratio. Omega n, we know this is undamped natural frequency. So we are interested to find the unit step response. The unit step response of second order system is the solution of y in equation number 4 when y of 0 equals to 0 and u of t equals to 1 for t greater than equals to 0. We know that the unit step response assume three forms, that is the damping ratio greater than 0, 0 to 1 or less than 0, depending upon the location of the algebraic equation. Now the algebraic equation, we know it can be represented as 2 zeta omega n s plus omega square n equals to 0. Again, this has been discussed by Professor Deepak Giri in the first course. Please revise your concepts if you are unaware about these equations. So this equation is generally known as the characteristic equation. We need these equations so that we can use in our MATLAB environment. Hence, we are revising this. And the roots are s1 comma 2 equals to minus zeta omega n plus or minus j omega n square root of 1 minus zeta square. Let us consider this as equation number 6. Here the frequency of oscillation is represented by this variable omega n into 1 minus zeta square, which is, we call it as damped natural frequency. Which is generally represented by omega d. So that is omega d equals to omega n 1 minus zeta square. Let us represent this equation as equation number 7. Now we know that the frequencies omega d and omega n have meaning only for the underdamped case. And for underdamped case, we know that zeta is 0 less than zeta less than 1. So, in this case, omega d is generally less than omega n, that is damped frequency is always less than undamped frequency. Now, we know that most of the practical applications deal with the underdamped case. So, our focus of attention will only be on underdamped case. So, let me write the solution of unit step response of the underdamped case. We will be plotting these responses in MATLAB. So, the unit step response of underdamped case is given as, I am directly writing the final expression. Again, this has been extensively covered in the first part of this course. Y of t equals to k into 1 minus e power minus zeta omega n t cos of omega d into t plus zeta omega n by omega d into sin omega d into t. This is applicable where t is greater than or equals to 0. We can also represent in terms of the phase angle. In terms of phase angle, let us represent this as equation number 8. In terms of phase angle phi, and when the input is constant, that is u of t equals to a, then equation 8 can also be written as, in terms of phase angle, y of t equals to a into k 1 minus omega n by omega d e power minus zeta omega n into t sin of omega d into t plus phi for t greater than or equals to 0. Let us represent this equation by equation number 9. So, where phi equals to tan inverse omega d by zeta omega n equals to tan inverse 1 minus zeta square divided by zeta. Now, we will use this equation for the second order system. We know that this mass spring damper system is represented by the second order. Let me draw the diagram here. This is the force F. This is the displacement represented by Y. This is damper C. This is K. So we know that equations of motion for mass spring damper system is represented as m into d square y of t divided by dt square plus c into dy by dt plus ks. Let me write here ks just to make it a little bit different from the steady state gain k, just to avoid confusion. Ks into y of t equals to f of t. Consider this as equation number 10. Now here y of t is represented as displacement of block of mass m from its static equilibrium position. F of t is nothing but the input force. Ks represents stiffness of spring. And C is the damper. So now the system can also be written in the form of equation number 4. That is y double dot plus c by m to y dot plus ks by m to y equals 1 by m into f. Let us take this as an equation number 11. Again I am dropping t term for convenience. Now if you compare this equation with the characteristic equation, we can easily get 2 zeta omega n equals to c upon m, omega square n equals to ks upon m, and k omega square n equals to 1 upon m. Now finally, solving for parameters, k omega n and zeta yields omega n equals to ks upon m, that is the square root, zeta equals to c by 2m, square root of m by ks, which can be further solved as c by 2 square root of ks to m, and k we can represent it as 1 upon m to m upon ks equals to 1 upon ks. Now we can easily obtain transfer function for equation number 11. This equation number 11, y double dot plus c by m y dot plus ks upon m into y equals 1 upon m into f. We will be considering taking the Laplace transform of equation number 11 with 0 initial conditions. Now we always consider 0 initial conditions whenever we take Laplace transform. So this can be represented as s square y of s plus c upon m s into y of s plus ks upon m into y of s equals 1 upon m into f of s. I can take y of s common from LHS. Y of s square plus c by m into s plus ks upon m equals to 1 upon m f of s. Finally, we can write the transfer function, that is Laplace transform of output to input variable y of s by f of s. Consider this as the transfer function tf equals to 1 upon ms square plus cs plus ks. Consider this as equation number 12. So this is the representation for the transfer function. Now with this we are ready to switch to MATLAB and implement this transfer function, this equation number 12, and plot the position and velocity using different methodologies. So in the next lecture we will be simulating this in position and the velocity in the MATLAB environment. Thank you.